So what next, João? Shall we wait a little bit or just to start the... Here is PK Sahu.
I guess that you can start, Milka, at least. Well, we have 3 minutes. So yeah, we are going to set up and then we start at 10.
Okay. Is there any communication to the people, any further information, João, that you want to share? Just to avoid this awful silence.
Okay. Yes, well, so for the lectures that are going to talk in the afternoon, yeah, I'm going to send a specific email after this morning section for you all, and then there it's going to have some instructions to access this Zoom webinar in as a panelist. So you are going to have more access to the controls like video settings and sound. And also for the participants, I kindly ask you to, or I kindly would like to ask you to write or type your questions here in the button Q&A instead of the chat. You can talk at the chat and share message with the other participants, but please, for questions, you use this button Q&A, because it's much more harder for us to see what is happening in the chat when it comes to questions. Okay, so please use this button. It's going to make our life easier here. I believe you can introduce the next lecture, Amilcar. Thank you.
Okay. So our next speaker is Professor PK Sahu. He got his PhD in mathematics from Sambalpur University in India, and he's associate professor at BITS Pilani, Hyderabad campus. His main subject is general relativity and cosmology, and he's going to talk to us today about wormholes in FORT, gravity, and general relativity. Please, Professor Sahu, you can start.
Yeah. So good morning, all. So am I audible?
Yes.
Okay. So my screen is visible?
Yes, also. Yes.
Yeah. So first of all, I will give my thanks to the organizers for giving me the opportunity to share my research, and in particularly Professor Santos for inviting me. So I will speak about the wormholes. In the beginning part, I will go for the basics of the wormholes. Then I will take one model of wormhole in modified FRT gravity, and I will compare this model with the general relativity. So these are my outline of the talk. Okay. So the first question is it possible the time travel through wormhole? So going through the time travel through wormhole, so I will just take you some movies where these wormholes are used. So if you go for the movie Contact in 1997, you can see Jodie Foster traveled to another planet by the help of wormhole. Then in 2011, if you go for the movie Thor, then there also a wormhole is used to travel between Earth and the Asgard. And in the movie Interstellar, the most recent in 2014, so the wormhole was used to travel farthest regions of the universe in search of the habitat planet. And these are basically the depictions of the wormholes and the interstellar travel, which is basically the science fascinate. So it is fascinate scientist and space enthusiast alike. But exactly we'll going through this talk, what are the wormholes and how they will work. Now, basically, wormhole is a hypothetical shortcut between two distant regions of the space-time. As if you go through Einstein's theory of relativity, he described about the cosmology through the space-time. So let me visualize this wormhole. So just let me take the figure. So if you go for 2D, you just take a piece of paper. Just take a piece of paper and fold it. Okay. So this is a piece of paper which is folded, and suppose one wants to travel from point A to point B. So instead of traveling throughout the surface of the paper, so he can make a hole here to reach the point from A to B. So that is basically the idea of the wormhole. So if you go for a intrinsically flat two-dimensional space as a folded piece of paper embedded in a higher three-dimensional space, like the next diagram. So where a tube connects two distant points A and B on the paper. So the length through the tube, that is basically the wormhole, can be much less than the distance from A to B along the paper. So this is basically a shortcut distance between 2 points in the paper. So the same idea was used in the wormhole to connecting two distant regions through a shortcut. Then if you go for 3 dimension, so a full 3-dimensional wormhole would have entrance and it has an exit. So there are 3-dimensional spheres rather than 2-dimensional ring-like mouths of the paper tube. So if you go for this figure, so there are paper. So if you go for it, you can see the mouth-like thing in the 2 dimension. But whereas if you go for this 3D, you can get these spheres. So this is basically the 2 mouths. So this is 1 mouth. The other end is another mouth, and these 2 mouths are connected by this throat. So this is the idea of the wormhole. So here there are 3-dimensional spheres rather than 2-dimensional ring-like mouths. So such lower dimensional human-friendly visualizations are termed as the MD diagram. So if anybody will go through the wormhole articles, they can see the embedded diagrams of the wormholes. And these are basically the wormhole image is usually as well known as the Schwarzschild embedding diagram, which is the wormhole analogy for a static non-rotating Schwarzschild black hole. Now, coming to the general relativity, so wormholes are basically to be filled with exotic matter. So this is not same as the dark matter. So this is the different, this which basically the exotic matter which does not satisfy the energy conditions, and there is a possibility of negative density. And this is known as the Einstein-Rosen bridge. It is a topological feature that will fundamentally be a shortcut connecting 2 separate points in the space-time or 2 separate regions in the space-time. And this contains 2 mouths, as I showed in the Evening diagram, and there is a throat connecting the 2 mouths, that is the separate points in the space-time like a tunnel. And this was introduced by the American theoretical physicist John Wheeler in 1957. And how the name wormhole came, the idea is this. So you take an apple and this worm wants to travel from one end to other end through the apple. So instead of this worm traveling in the surface of the apple, so what he can do, he can make a hole from one end and exit in other end. So that is the idea of the name wormhole coming from this picture. So that is what the idea what John Wheeler took in 1957. Now, these 2 figures are very much clear. If you take a piece of fabric and put some weight, and then due to gravitational attraction, you can get the sag. And this is basically the second figure is a black hole, supermassive black hole, which makes a tear like the wormhole. So this is the space-time tear, which we use to say the black hole. And these 2 regions would meet and form a wormhole connection. Basically, if there is a tear in the space-time and this tear is the wormhole, and these 2 regions will meet and they form a wormhole connection, which is known as the throat of the wormhole. So these wormholes are not black holes, because if you go for the black hole, we used to say that everything can enter, but nothing can exit. So that's why we always used to tell that this is a one-way trip. Anybody can enter, but nothing can exit. But if you go for the wormhole, it is two-way. There is an entrance and there is an exit. So one can enter and exit from the wormhole. So then the next question is, do wormhole actually exist? So there is no observational evidence for the wormholes currently exist. It is basically a mathematical solution of the Einstein's field equation in general theory of relativity. Like the black holes, which was observed in 2019 April 10 by Event Horizon Telescope, that there was black holes. At the same time, there is no observational evidence for the wormholes. Only it is a mathematical solution to the Einstein's field equation in general theory of relativity. And these wormholes made completely a normal matter with positive energy density, and inherently it is unstable, and there may be it would be likely to collapse in the presence of nearby matter or matter that tried to traverse through the wormhole. So basically we'll study the stable traversable wormholes, which exist, and their entrance and exit were held open by exotic matter with a negative energy density. Then coming to the history, this was started by Albert Einstein in 1916. Then Flam in 1916 got the white hole solution. Then Schwarzschild, which we famous for the Schwarzschild solutions, the static spherically symmetric Schwarzschild solutions. So the first exact solution to the Einstein field equation in 1916. Then in 1921, the German mathematician Weil first proposed the wormhole theory. After that, this is the cover of the book. A wormhole is a theoretical passage through space-time, which is known as the Einstein-Rosen bridge in 1935. So Einstein and Nathan Rosen gave the proof for the wormhole. So after that, in 1948, Gödel got the time tunnel is possible. Then the famous one is the Wheeler, who gave the name in 1957 as wormhole. Then after 30 years, then after that there is not much work after 1957. Then the promising work after 30 years come by Morris and Throne in 1988. And that is what they gave the most promising wormhole as tool to teach the general relativity, and they proposed the traversable wormholes. Now coming to the type of wormholes. So by the name of the physicist, there are wormholes called as the Schwarzschild wormhole, Lorentz wormhole, Morris Throne wormhole, Ellis wormhole, then Matt Visser wormhole, because he proposed the Australian scientist Matt Visser also proposed some wormholes named after their ideas. But there are multiple ideas about the different type of wormholes based upon their functions. So primarily, there are 6 type of wormholes exist. So these 6 types are the traversable wormhole, which is the most promising, and the more research is going on this, and this is basically these traversable wormholes are used in the science fiction and the Hollywood movies. Then the next one is the non-traversable wormholes. So these are basically nothing can pass through it. Either the wormhole will collapse very fast. So it only has an entry point, but there is no exit. Then coming to the next one, the one-way. The one-way wormholes are one-way trip, meaning you can only travel through them and you cannot separate the wormhole from the return trip. Then coming to the black holes. Yes, black holes are actually types of one-way wormholes that everybody knows that anything can enter a black hole, but due to its intense gravitational pull, nothing can escape. Then the next one is white holes, so which is very easy. Now coming to the other wormholes, there are two-way wormholes. Basically, the wormholes are round trip, as I told from the beginning. One can enter and exit. Then intra-inverse. So the intra-inverse wormholes are located in our own inverse and are traveling from one point to another point within our inverse. Then inter-universe. The inter-universe wormholes connects from one universe to another parallel universe. And this is a basically a diagram of the spacecraft traveling through a traversable wormhole, which I took from NASA's picture. Now coming to the idea, so we want to create a traversable and stable wormhole for use in space travel. And these are the intra-universe, that is two-way traversable wormholes. So this is basically just I show that how Einstein is going through Earth to our nearest galaxy, Andromeda galaxy, through the wormhole. Okay, now come to the basics. So this is basically when you go for study of this wormhole, they are generally these are obtained by solving Einstein field equation in a reverse direction. We used to solve this in a reverse direction. That means first consider an interesting and exotic space-time matter. So this is the space-time which you have to beginning you have to consider it. Then go for the matter and find the respective geometry. And it is interesting to note that it allows effective superluminal travel. So that is what the basic idea of the wormhole. So this is the equation 1 is the spherically symmetric wormhole metric with Schwarzschild coordinates is given in equation 1. So there are two unknowns, A of r and B of r. So A of r is known as the redshift function and B of r is known as the shape function. So through B of r, so we'll measure this travel through B of r, the radial coordinate, the shape function, and r is the radial coordinate which is from r0 to infinity. And this r0 is known as the throat radius. So there are 4 minimum conditions which a wormhole metric must satisfy. So the first condition is known as the throat condition. That means at the point r0. So B of r0 is equal to r0. Then the second condition is known as the flaring out condition. So the flaring out condition says that the derivative of the shape function with respect to the radial coordinate. So the derivative of B of r at r0 must be less than 1. So this is known as the flaring out condition. Then the third condition is known as the flatness condition. So the flatness condition says that so B of r by r tends to 0 when r tends to infinity. And the last condition is known as for the redshift. So it is on the redshift function that the redshift function must be finite everywhere for the traversable wormholes. So these are the 4 minimum conditions where a wormhole metric has to satisfy. Now coming to the exotic matter. So from the beginning, I told that it is not same as the dark matter or antimatter. It is basically, it contains negative energy density and a large amount of negative pressure and mass. And such type of matter has seen in the behavior of vacuum states as part of quantum field theory. So in case of these Schwarzschild wormholes, it was found that it would collapse too quickly for anything to cross from one end to the other end. And in traversable wormholes would be only be possible if this exotic matter with negative energy density will be used to stabilize it. And for the development of wormhole structures, an exotic fluid is required which violates the null energy condition. So this is the important point in this wormhole theory, because they have to violate this null energy condition out of the 4 energy conditions. So next I will go for the energy conditions. So there are 4 energy conditions. They are the null energy condition. Okay, so the energy conditions are basically the Raychaudhuri equations that describe the behavior of the geometry, that is whether this is time-like, space-like, or light-like curves. So it is commonly used in the general theory of relativity to study the singularities. And mostly if you go for the singularity problems in the Penrose or Stephen Hawking's, so you can see the singularities there. And they use this energy conditions are used very much there. Now, the first energy condition is the null energy condition, which says that the sum of the density and pressure are greater than equal to 0. So, which is presented in equation 5. This is the minimum requirement which is obtained from the strong energy condition and weak energy condition, the SEC and WC. So, second one is the weak energy condition. So, the weak energy condition is the addition of null energy with the density always positive. Then the third one is the strong energy condition. And if you go for the 1998 paper by Matt Visser, which says that due to the acceleration of the universe, the strong energy condition has to be violated. And the last one is the dominant energy condition, which tells that the density is always greater than equal to the magnitude of the pressure. So these are the four popular energy conditions which is used in the singularity problems. Now coming to the phantom era and the wormhole geometry. So basically, if you go for the accelerated expansion of the universe through the equation of state parameter, then we used to tell that when the equation of state parameter p by rho is equal to -1, then it is the standard cosmological model or the lambda CDM. Then from the 0 to -1, we used to say that it is the quintence region, and less than -1 is known as the phantom region. So basically, the singularity problems always in the phantom era. Okay, now coming to the wormhole solution, as I told, it is a reverse engineering process where we have to consider the wormhole metric and the matter. So the matter content here is represented in equation 9, which is the energy momentum tensor for the anisotropic fluid. So here rho stands for the density, Pt is the traversal pressure, and rho is the radial pressure. And here this Ui, Uj are the 4 velocity vector, whereas Xi, Xa are the 4 velocity vector. So radial unit 4 vector. Then the matter Lagrangian. So the matter Lagrangian, as you know, you can take it is the density or the pressure. So the matter Lagrangian is here -P, and which is the pressure, and P stands for the radial pressure plus 2 transverse pressure. Then let us go for the FRT gravity. So this FRT gravity basically proposed by Harko and his team in 2011. And in that 2011 article, they have proposed 3 forms of FRT gravity. So out of the 3 forms, the first 2 forms are the linear form, and the third one is the nonlinear form. So out of these 3 forms, we have taken in this article this first form. So where f of rt is called r plus 2ft, and f of t is the function of the stress energy tensor T, which is equal to lambda t. And here lambda is the model parameter. And if you make this lambda is equal to 0, then this FRT gravity will reduce to general theory of relativity. And the FRT gravity field equation is given in equation 10. Now, taking the metric, the wormhole metric with the energy momentum tensor, we can get the Einstein field equation for the FRT gravity, which is given in equations 11 to 13. Now we can see from 11 to 13, there are 3 equations with 4 unknowns. So 2 pressure, then density, and the shape function. So there are 4 equations, 4 unknowns with 3 equations. Hence, to get a deterministic solution, we have assumed some extra conditions. So first of all, we proposed a new exponential function, first time in the literature, by me and my collaborators, Pedro Morias and my 2 students, which is published in last year, December, in Chinese Physics Letter. So this equation 14 is the new shape function which was proposed by us. And if you see the figure 1, this shape function, which is called the exponential shape function, satisfies the minimum requirement of the wormhole condition. So the 4 conditions was given in this figure 1, and one can observe that all the 4 conditions are satisfied by the proposed exponential shape function. And here we have taken the wormhole throat R0 is 0.5. Now, taking this shape function, so our pressure and density with equation of state parameter omega r, which in the radial coordinate is PR by rho, are given in these equations. Now, going through the figures, you can see that the equation of state parameter omega is below -1. So which indicates that this is in the phantom era. Now, coming to the next figure, in figure 3, you can see that all the energy conditions are validated except the strong energy condition. So the violation of strong energy condition tells that the model is accelerating model, whereas it is satisfies all other energy conditions. So the point here is due to the modified gravity, because the property of wormhole geometry is it has to violate the null energy condition. But in this case, you can see that the null energy condition is satisfied. That means there is no exotic matter in this model due to the modified gravity. Then we can see what is the behavior in general theory of relativity. Now, at the same time, we make lambda is equal to 0. So when you make lambda is equal to 0, this FRT gravity reduces to general theory of relativity. Now, if you see the behavior of the energy conditions in general theory of relativity, which is given in figure 4, that all except one, the null energy condition in radial coordinate, all other energy conditions are violated. So this proves that there is exotic matter in general theory of relativity in the proposed wormhole metric with the shape function. So it validates that this is theoretically valid as it violates all the energy conditions except one. So hence our proposed model is validated through general theory of relativity, presenting that there is exotic matter. But if you see in the modified theory of gravity, that is the FRT gravity, so here all the energy conditions are validated except the strong energy condition. And as per the article of Matt Visser in 1998, the violation of strong energy condition indicates the acceleration of the model, which is as per the current expansion. Now, coming to the conclusion, basically, as I explained, the wormholes are tube-like structures which are shortcuts, and it connects to distant regions in the universe. If their geometrical structure was not singular enough, then according to the general theory of relativity, wormholes are expected to be filled by exotic matter. Then due to the lack of observation, the wormholes makes one unable to predict exactly some of their geometrical and material properties, such as the shape function and the equation of state. So in the present article, we have proposed a new shape function called as the exponential shape function. And on the other hand, we did not need to assume any particular form for the wormhole equation of state, which was obtained from the model rather than imposing it. And before going any further on this discussion, the equation of state parameter obtained, we should mention that for exponential shape function, which is given in equation 14 and in figure 1, it satisfies all the required 4 conditions for the traversable asymptotically flat wormholes. And in this case, our equation of state parameter omega also constructed, and it was there in the phantom era. That is what in the figure 2, our equation of state parameter is less than -1, implying that it is in the phantom era, and there may be possibility of big rip singularity. Now coming to the third figure, which is in FRT gravity about the energy conditions, it shows that the null energy condition, weak energy condition, all the conditions except the strong energy conditions satisfied. Then the violation of strong energy condition, already I told, it is as per the accelerated expansion of the universe. Now, these are the few references which are used in this article. And thank you all for your patience to listening me.
Okay, thanks a lot, Professor Sahu, for the nice talk. I'd like to ask if anyone has a question to Professor Sahu. Questions?
Yeah, Amilcar, I have a question.
Okay, go on.
Okay, so before the question, thank you, Sahu. It's really a pleasure to see you and see you well. And I'm really happy to have you here. Sahu and we started, I guess, in the last year to collaborate each other, and it's really a pleasure to have you here with us. And then my question is, I saw your graphics about the energy conditions for the FRT model when you submit it to a wormhole solution. And I guess it's really interesting that it seems to make more favorable to have the wormhole solution than in the general relativity, at least in respect to the energy condition. So I remember that the point when Harco put this component of the energy momentum tensor in the theory for gravity was that it is related with vacuum energy. So it seems that the vacuum energy in such way it prefers wormhole solutions than the standard general relativity model with the cosmological constant. So do you have any kind of comment about this?
So basically, this, as I told here, we proposed a vacuum solution. Basically, as you mentioned also, yeah. So this is the source fluid, which is basically go for the vacuum type of solution, which we proposed from the beginning. And as you mentioned that about the lambda CDM, okay. So when you go for the singularity problems, basically the singularity problems always goes in the phantom era. So when you go for the phantom era, then the equation of state parameter must be less than -1. And our lambda CDM model approaches to -1. So the singularity problems, as per the literature, they are always comes in the phantom era. So I don't think it will approach to the lambda CDM model.
Okay. So thank you. It's really interesting the results that you presented, and thank you so much for the presentation. It was a pleasure.
Okay, thanks a lot. Is there any further questions? So
I mentioned that I collaborated with Professor Santos mostly 1 year, and we published 2 articles, one in Physical Review D and another in European Physical Journal Plus. And the third article is under review.
Great.
So, yeah, it is a nice collaboration and a fruitful result also, because publishing in Physical Review D, one of our article in this year. So this year we published already 2 articles, and the third one is in under review. So thanks, Professor Santos, for our collaboration and inviting me to this platform, because my background is mathematics and I'm giving a talk in the seminar physics. So really it is a pleasure for me. Thank you.
Okay, thanks to you for the time and to share the knowledge with us. Thanks a lot. So, João, what should we do now?
Okay, so again, thank you, Sahu. And now we are going to have a break time. We have 30 minutes of break, and then we go back live at 11 here in Brazil, 11 o'clock here in Brazil. with our next presentation, which is from Professor Philip Bull. So thank you again, people. And well, you can stay at the room if you want. You don't need to leave. The web link to access this room, it is going to be the same web link along the entire event. So you can stay in the room if you want. But I'm going to just stop the recording and also the live transmission. Okay, so we go back in live at 11. Thank you.